to the Nobel Prize in Physics on 2020. Our speaker today is Dr. Reinhard Schödel. But before introducing him properly, I would like to remind you, please keep your microphone mute. And if you want to do any question, you can write it on the chat. And at the end of the presentation, we can keep some more questions, and even you can make directly your question to the speaker. I would like to thank Reinhard Schödel for accepting our invitation to this colloquium. Dr. Reinhard Schödel obtained his diploma in geophysics at the Ludwig Maximilian Universität in Munich in 2000, and then his PhD in physics astrophysics at the same university, being predoctoral researcher at the Max Planck Institute for extraterrestrial physics in Munich in 2004, under the supervision of the Professor Genzel, one of the researchers that received the Nobel Prize in Physics 2020. Then from 2003 to 2007, he works as postdoctoral researcher at the Institute Physics 1 at the University of Cologne. In 2008, he joined the Institute of Astrofísica of Andalucía thanks to a Ramón y Cajal Fellowship. And in 2014, he obtained his ERC Consolidator grant at the same institute where he leads the Galactic Center Group. Dr. Schödel has not only worked with Professor Genzel, but also collaborated with Professor Andrea Ghez, also awarded the Nobel Prize in Physics. So he is one of the best researchers that know the Nobel Prize winning works focus on the observation of the black hole in the galactic center. So please, Reinhard, you can go ahead to this colloquium with the title, The Nobel Prize in Physics, the massive black hole at the center of the Milky Way. Thank you very much.
Thank you very much for this nice introduction, and thanks again for the invitation to give this talk. It's my pleasure to talk about this topic. So I'm Reinhard Schödel from the IAA in Granada, Instituto Astrofísica de Andalucía. And yes, so we will talk about the black hole at the center of the Milky Way. The black hole, the massive black hole, or maybe we can also call it the central black hole of the Milky Way, because we know there's hundreds of millions of black holes in our galaxy, but there's only, as far as we know, one massive or supermassive black hole, that is Sagittarius A star, which is located right at the very center. So let's dive in. Please feel free, since we're not a big audience, feel free to interrupt me and if there's any brief questions. For longer questions, we can treat them at the end of this talk. I know this is not, so most of the people in the audience now, they are not much into astronomy, astrophysics, I guess. So if there's anything, some basic concepts you need me to explain briefly, please interrupt me. I hope, nevertheless, that everything will be clear. So this are some pictures of the universe at large. So looking into deep space outside of the Milky Way, we deal with hundreds of billions of galaxies in our universe, and full of stars and gas, and they're also full of neutron stars and full of white dwarfs and full of many stellar black holes. Stellar black holes are the remnants when very massive stars end their lives. But there's also one thing, that basically all major galaxies have massive black holes at their very centers. Massive, or sometimes also called supermassive black holes. And how do we know this? I mean, they're black holes, they're not easily visible, but basically in the 1960s, radio astronomy got ever better, and very, very strong extragalactic radio sources were detected. And then with interferometers, with large radio interferometers, one could see that these radio sources very frequently were connected to jets, as you see here. So this is, if you have here a massive galaxy, and then at the center you have something happening, way too small to resolve it, but then you would have you would find radio jets that are bigger than the entire galaxy. And obviously you need some very powerful engine to drive that. Later on, not much later, a few years later, strange objects were also discovered in the visual regimes. They're called QSOs, or quasars, quasi-stellar objects. They look like stars, but they're very far away. They're extragalactic objects. And given their distance and their brightness, they are basically the brightest things in the universe, at least the brightest things that shine permanently in the universe. And it was a big problem. So for a few years, there was a big confusion. What could drive the energetics of these objects? The problem is if you have these enormous energies, it's not easy to produce this radiation. If you have hydrogen fusion, you can convert as much as 0.7% of the rest mass of the involved nuclei into radiative energy. But that's not enough. And soon, however, it was theorized that we are dealing with supermassive black holes that accrete matter. And in fact, in a thin accretion disk, where the matter slowly spirals into a black hole, you can actually radiate easily 10% of the rest mass as energy. So this is more or less, apart from annihilation with antimatter, that's the most efficient way you can convert rest mass into electromagnetic energy. So soon it was discovered that these quasars are everywhere in the universe. And it was also clear that in the past of the universe, there were far more of these quasars. That was because the universe, let's say, was far more active 10 billion years ago than nowadays, because the universe is expanding. So the distances between the galaxies become greater. There's less star formation in the present day universe, and there's less gas accreted to the centers of the galaxies. So this results that in the local universe, in the present day universe, there's very, very few of these active galactic nuclei of these quasars nearby. However, pure logic says that these supermassive black holes must still be there, even if they're dormant. But the problem is, a black hole that does not accrete any matter is extremely hard to detect, because black holes, by definitions, are tiny objects. Even if they have billions of solar masses, they're really tiny compared to the galaxies. So it's very hard to detect them, either by gravitational influence on their surroundings or by accretion of matter. Here, by the way, you see from 2018, from the Event Horizon Telescope, that is the first image of the direct surroundings of a massive black hole. That's the one in the galaxy M87. It's an elliptical galaxy. It was found there were also these strong jets in there. And now the Event Horizon Telescope, which is millimeter radio telescopes all around the Earth synchronized together, they could resolve this. And you see this dark, it looks like a donut. You see this dark shadow in the middle, and the dark shadow is because of relativistic light bending around the black hole. So now the big question is, how do you find these black holes, these supermassive black holes, when they do not shine brightly, and how do you actually prove that you really are dealing with a black hole? I mean, theory and the data tell you it's a very probable hypothesis, but you want to push this stuff to the limit, as always in physics. So the question is there something like that in our own galaxy? So this is the Milky Way, seen in the night sky from Chile, from Cerro Chajnantor. And you see we live in a disky galaxy because it's a very flat. So you see it we live inside this galaxy. So we see this flat shape and a central thickening. That's the so-called bulge. And you see this is very important for this work. There's a lot of dark lines. So any one of you has ever looked at the Milky Way, you know it's not just a nice Milky Way, but there's lots of dark patches, and these dark patches are interstellar gas clouds, and they're full of dust. They're extremely dusty, and this is opaque, so visible radiation cannot penetrate that. So basically, visible light is not good to explore the Milky Way. This is why it's being done in the infrared nowadays. This is the location of the center of the Milky Way, and it's right behind such dust clouds. So we cannot easily see anything there. But right after the Second World War, it was already discovered that the center of the Milky Way is the brightest radio source in the sky. This is the Milky Way seen from the outside. We have these spiral arms where star formation takes place. We have a bar in the middle. The sun is roughly here at about 26,000 light years from the center. And we're looking down the disk. And when we do this, then in the infrared in the plane of the sky, it looks like that. So we have this flattish things due to the Milky Way disk. And then in the middle, we're thickening, which is due to the bar that we see edge on. Now, if you want to look closer in, we look at this central image here. Sorry for the units here. I know the units is something that is very hard to transfer from one physics field to the other ones. We always talk of kiloparsecs. So 1 parsec is 3.26 light years. So this is a few thousand light years across. So this is the galactic center now seen with an infrared telescope at 5 microns roughly. This is actually, you have to go to space to take these kind of images, because in the thermal infrared, which is beyond 3 microns, it's very hard to do imaging from the ground because everything is warm and you need to go to a cold place and cool your detector with helium. This is best done in space. This is now, you see the galactic center here. It's full of stars. Even in this infrared light, you have these dark clouds. Now, if we look this central dot here with the Hubble Space Telescope, this would be a view of this field in the nearest galaxy, the Andromeda galaxy, while on the right-hand side, you see how we see the center of the Milky Way. And you see this is really different. The center of the Milky Way, you see thousands of stars, whereas even in the nearest extragalactic case, you just see diffuse light. So we can do stuff in the Milky Way that we can do at no other place in the universe. So the big question now is, so this, by the way, this is roughly 3 full moons across this image. So here we have a nuclear star cluster. This is a few tens of millions of stars at the very heart of the galaxy. And if we go even further in, this is now with the best technology we have, super sharp image. I will explain that in a minute. You see the concentration of stars at the heart of the Milky Way. And what was discovered now in the 70s, if we look at now just this field, so this is in an angular scale, it's roughly, it's 15 by 15 arc seconds of arc. So this is already, the size of this field is already smaller than what your eye can resolve. So the resolution of the human eye is 1 arc minute roughly. So if we look at this now with radio imaging, we do not see the stars, but we see either stuff that sends synchrotron emission from fast electrons and magnetic fields, or Bremsstrahlung from warm ionized gas. And here you see lots of diffuse stuff that is gas, that's ionized gas. You see some brighter sources, but in the very middle, you see a white, extremely strong source. It's non-thermal in its nature. That means you have there electrons that basically move at the speed of light in a magnetic field, and they create very strong synchrotron radiation and radio. And this object was discovered in 1974, and it has the terminology Sagittarius A star. The star is an asterisk, and it was meant to indicate an excited state, basically like in nuclear physics. It should indicate that it's a special radio source within the entire complex of Sagittarius. As I said, it's non-thermal, so it's nothing like a star or gas or whatever. And it was also discovered that it is extremely small, smaller than the Earth's orbit around the sun. And this was discovered in the 70s. It was the heyday of quasars, of these extragalactic quasi-stellar objects. And it was soon hypothesized that this may be the manifestation of the Milky Way's central black hole. And this was now the big question. Is it or is it not? Because it was very faint, so it could be other things. So how do you show that something is a black hole, you have to show that there's a lot of mass enclosed in very small volume so that you can exclude any alternative hypothesis. In space, in astronomy, you measure masses by moving objects. Basically, you take test bodies in a gravitational field and map out the gravitational field and calculate the mass. As, for example, you can easily compute the mass of the Earth from the orbit of the Moon, or you can calculate the mass of the Sun from the orbit of the Earth around the Sun. And the same thing was now, the idea was using the stars that are in the center of the Milky Way as test bodies to see whether their motion shows us that there's a massive black hole. And this is what the Experimental Nobel Prize in Physics 2020 was awarded for. So there's two groups who undertook this work. So it was Andrea Ghez from UCLA, University of California in Los Angeles, with her group, and Reinhard Genzel from the Max Planck Institute for Extraterrestrial Physics. So behind these two persons, of course, there's big teams, changing teams along the time, because the entire experiment took more than 2 decades, huge research infrastructures and cameras and instruments, of course. So what are these observational techniques that were applied? So first of all, I have already mentioned that several times in my talk, and let's iterate again. The problem is, how do you even observe a star at the center of the Milky Way? It's not easy for 2 reasons. One is the so-called interstellar extinction. I've said already that if you look at the Milky Way, there's these very, very dark clouds, and light cannot penetrate these clouds because of the dust in them. Here you have down here I have put a scale of electromagnetic wavelengths. So here's in microns from 0.38 to 0.74 microns visible light. And this is an image in visible light towards the center of the galaxy. And we go out now here to the infrared, 1.3, 1.7, and 2.2 microns. In the visible light, even at the very edge of what one can see, the attenuation is 10 to the minus 13. So that means from 10 to the 13 photons emitted in the visible light at the galactic center, about 1 arrives at Earth. So it's impossible to observe anything. If you go now to the infrared, so this is 1.3 micrometers here, things become slightly transparent, but we're still dominated by dark clouds. If we go to 1.7 microns, we see that there's actually one relatively bright region turning up. And at 2.2 microns, it's finally relatively transparent. We see that where the blue cross is, there's some very bright object that is the nuclear star cluster. And this is actually the location of the galactic center. So this is the first thing you need to observe. You need infrared detectors. And this is why this kind of work could not be done before the 1990s. Actually, only towards the end of the 1990s, we had good infrared detectors. So Hubble Space Telescope was one of the first ones with a good infrared detector. The second problem is it's full of stars. So it's so full of stars that if you take a normal telescope and look at there, you are limited by the Earth's atmosphere. So theoretically, the size of a telescope, the bigger the telescope, the sharper the image. So the size of the telescope gives you the diffraction limit. And if you build a big telescope, you can get very sharp images. In practice, however, looking through the Earth's atmosphere is like looking from the bottom of a swimming pool outside. Everything moves, and the turbulence in the Earth's atmosphere mixes packages of different refractive index in the air because of different temperature, and it blurs the image. And this is what a blurry image of the galactic center looks like. This is from the ground under very good atmospheric conditions. This is if you go to space and use the Hubble Space Telescope, it looks a lot better. The problem is, though, the Hubble is small. The Hubble has only a 2-meter mirror, and that is not good for this kind of work. So in the end, you want to have something like 8 to 10 meter mirrors on your telescope. We only have that on the Earth. But there's special technique to overcome the problems of the Earth's atmosphere, and then you end up with very sharp images from the ground. This is equivalent to being able to read the newspaper from 100 meters distance. So you need this high angular resolution. You need to go to the diffraction limit of huge astronomical telescopes. To illustrate this a bit more, because it's quite interesting, and actually there's similar problems in microscopy, for example. Also eye doctors deal with these problems. It's all the time when you have light propagation through a turbulent medium. So this is actually what you see here on this movie. This is one single star, and each image in this movie is about 100 milliseconds exposure. And you see the star does not look like a star at all. It looks like a so-called speckle cloud. It's an interference pattern. It's basically, if you take your laser pointer, shine it against the wall, you see a lot of hundreds of bright dots. That's the speckles. And the same happens when you have this random diffraction pattern of a star through the atmosphere. There's one way to get sharp images out of this. You can actually take a series of these short exposures, and this is what was done at the very beginning of this work, and then you do a reconstruction of your image on the computer afterwards. There's several algorithms how to do this, and then you can end up with sharp images at the refraction limit of the instrument. The signal to noise is not optimal, but it's good enough for the early work. The next step was, if you actually have a deformable mirror that can correct the incoming light in real time, that can basically bend the wavefront again, counter the Earth's atmosphere, then you can get very sharp images. So if left is the oldest images, basically taking the oldest speckle imaging algorithms with reconstruction of the computer, the middle is a better algorithm that I implemented 10 years ago. And now on the right-hand side, now you see when you use new technology that is basically standard now since roughly 10 or 15 years, it's called adaptive optics, which I will explain in a moment, and it allows you to take long exposures with a stable image. This adaptive optics basically gets, you have a telescope, you have light coming from space, and when it enters the atmosphere, the light gets distorted. So what you do is you have a beam splitter, and part of the light, basically the infrared light, goes to your camera, while you use mostly the visible light to measure atmospheric turbulence, then invert the signal and steer a deformable mirror. It's a very thin mirror, depending, less than a millimeter thick, with piezo crystals at the end, and then at about 100 hertz frequency, you create a closed loop and you stabilize this image. In practice, it looks like this. You go from, so you first have this speckle pattern, and then you stabilize the image. So here you see a triple star at the end. And this kind of work was done with these instruments. So the European telescopes are in Chile. You need to go to the southern hemisphere to have a good view towards the constellation of Sagittarius, while the American team used the W.M. Keck telescope, the 10-meter telescope on Mauna Kea in Hawaii. So the idea was to measure the positions of stars with extreme precision, do these measurements repeatedly, and then see how these stars move and whether the movement of the stars indicates anything about there being a massive black hole. One other problem here is stars are visible in the images. The black hole is not visible on these images, at least not in these early images, because it's very faint. So where is actually your black hole? Or a different question to pose is, if everything moves there, where is the origin of your coordinate system? There's no ruler in space, so it's very hard to do a measurement when everything moves. We do not have a nice laboratory where we have an optical bench and we can and we have a nice reference system. The trick to do this, and that was done by radio astronomers, so Carl Menton and Mark Reed and their collaborators, they measured with radio interferometers, with intercontinental interferometry, the positions of several very bright stars. These stars are so-called maser stars. They have actually they have radio maser emission in their atmospheres. They're old stars, giant stars. And they are visible both in the infrared and in the radio, and one can measure extremely precisely their position with radio telescopes. And since the black hole is visible, or the putative black hole was visible in the radio as well, you know exactly the position, the relative position between these stars and the black hole. And this is how you solve this problem. So this is how you know then that the position of your black hole relative to these stars. Then you have just basically, then you just simply take your images from different years. For example, here you see images from the year 2003 and the year 2012. Again, we're moving on, we're dealing with very small angular scales here. So both images are 13 by 13 seconds of arc. That is very, very small. And this is now superposed. This is the image from the year 2003. Here you see this bright guy here is actually a star that is used for the adaptive optics. And it's also one of the reference stars from radio astronomy. The black hole is the origin at 0, 0. This is the information that we get from combining radio images and infrared images. And now we see what happens in the year 2012. About 10 years later, it looks like this. So you see two effects here. First of all, the image quality is slightly different between the images. But if you look close to 0, 0, close to where I hope you can see the arrow of my mouse, oops, you can see that actually the stars are not exactly at the same position. And it's quite amazing because you can see actually how the stars have moved. Although these things are at 26,000 light years distance. And that is because they move at incredible speed. So most of these stars move at several hundred kilometers per second. And now such images have been taken actually since the middle of the 1990s. And this experiment is still being done today. So each year new images are being taken. So now you can get the velocity of these stars from position over time. And it looks like this. So this is an image, and each blue arrow shows you the direction of motion of a star, and the length of the arrow shows its speed. And here you see that at the center of the image, all the arrows are very long. So this is where our putative black hole is. The stars move very fast there. And in fact, if we make a one-dimensional plot now of okay, well, no, I don't show more of this. And actually, one can see that this follows a Kepler law. So the increase of the velocity dispersion from out here towards Sagittarius A star follows a 1/square of the radius law. This is exactly as in the solar system, the law that makes the planets move around the sun. This is what you expect in a gravitational, when point masses move in a gravitational field of a point mass. So this was the status basically in the beginning. That was basically towards the year 2000. At the year 2000, we knew that there's probably a point mass of a few million solar masses. However, it got better. In the year 2002, a decisive thing happened. Here you have an incredibly small scale. So each of these images is 1 arc second. 1 arc second, that is basically the size of a star imaged through the Earth atmosphere if you do not have any additional technical help. And here you see that the green cross is the position of Sagittarius A star. The green cross shows you where the black hole, the putative black hole is. We see in May 2002 on the left image, you see that there's a relatively bright star right on top of this green cross. The right image has been taken just 4 months later, and it shows you that this star is not on the position of the green cross again. Actually, this means the star has moved at an incredible speed. It actually has moved at several thousand kilometers per second between these two images. And the good thing is this star has been observed since the 1990s. And if you now overplot the positions of this star onto this image, so the first white dot here is from the year 1992, then we are 1995, 6, etc. The year 2000, 2001, and 2002, and 2003. And one can fit an orbit through this, a Kepler orbit, in fact. This star is called S2. The Americans call it SO2. They have a different way of numbering their sources. And what happened then in 2002 is that this star passed by the position of the black hole. And that was the key measurement in this entire work, because for the first time, one could fit really a full orbit to this. What you see here in white is the measurements with the error bars. They get much better on this hand because from this point, so this is the year 2002, and this is year 2003, 2004, and then the technology changed there, and we have adaptive optics now, we have better technology and much smaller error bars. The blue circle is the focus of the ellipse. The yellow cross is the error box of the position of the black hole between radio and infrared. Basically, that's the error box of the relative registration of the two frames of reference. It's an ellipse. We can then immediately use Kepler's laws, and we see that we need 16 years. The stars need 16 years for one orbit. It approaches the black hole to just within 17 light hours. This requires, so we can now use just Kepler laws, and the Kepler law tells us that we require a point mass of 4 million solar masses at the focus of Sagittarius A star. And one more information, since this is a perfect Kepler orbit, it means that all the mass must be enclosed within this orbit. So the pericenter, the star approaches the black hole to 16 light hours. This is not much bigger than the solar system. So we know that these 4 million solar masses must be compressed in a space that is smaller or as not much bigger than the solar system. Basically, the red circle is the solar system projected towards the black hole. So thanks to Johannes Kepler, we know now that there's a lot of mass at the center of the Milky Way, and this mass is mostly invisible. It's extremely dark. And this is the answer that we have, because then now we can think about what can this be? So if one thinks what this can be, the problem is you have to think about what it cannot be. So you think about various hypotheses, possible things that could be at the center of the Milky Way. So you can come up, you can say, well, there can be dark objects concentrated in a very dense cluster. So for example, rocks or neutron stars or stellar mass black holes. And there's a nice theoretical work from Maus et al. 1998 that gives basically, he produced this diagram, and it's on one axis, it's the total mass of your object. On the other axis, you see the density. You don't need to go into detail. It's the density of your mass in solar masses per cubic parsec. So cubic parsec is 3.26 times 3.26 times 3.26 light years. In all extragalactic systems, the density is so low that the lifetime of these things is forever. So if you have a dense cluster of things moving in their own gravitational field, something limits the lifetime of such a configuration. It's like a star cluster. It will either evaporate or it will collapse to a massive black hole. And you can calculate this lifetime. So in all extragalactic measurements that we have, the lifetime is longer than the lifetime of the universe. But here in the galaxy, we knew already in the 1990s that whatever there was, that mass density was so high that no cumulus, no cluster of astrophysical objects would live longer than 100 million years. Now, after having measured the orbit of the star S2 in the year 2002, the mass density that we knew was much higher by 3 orders of magnitude. And that meant that anything that is there that is not a massive black hole, that is a cluster of something, cannot have a lifetime longer than 1 million years. And that is only one of many different measurements. We also see there's no light emitted. There's a non-thermal radio source. We also know that particle physics, very hypothetical things like neutrino balls don't work. So that was basically the measurement that excluded any alternatives to a massive black hole. That was published in a letter to Nature in 2002 by Reinhard Genzel's group. As you can see, I was very lucky to be the first author on this one. I I did my fair share of work. I was a PhD student, but it was kind of to give some insight on what happened. That was, we had a reunion, a meeting, and then, yeah, we have to write a letter to Nature, and who's going to be the first author? Reinhard was fine. He said he's the group leader, so he could be generous on that. He knew that everyone knew it was his work. Thomas Ott was a postdoc who actually mentored me during a lot of my beginning of my thesis. There were other people there like Andreas Eckert from the University of Cologne, who were not from the Max Planck Institute, so for political reasons they couldn't be. And then Thomas said, I have already a paper, you have one, you need one for a PhD, and this is how I ended up as first author, just to tell you how these things go in reality. So that was really nice. I mean, as I said, I really contributed my fair share, but being first author on that was also an act of grace by the other authors. The team by Andrea Ghez had the same measurements with a different telescope at the same time. They were slower in publication because they have a different philosophy of approach. They really are more meticulous, and they really work very, very hard on the data to exclude any systematic errors, because actually I have also learned over the years that most of our work is dominated by systematics. And they, at the same time, made the first measurement also of the line of sight velocity of this one star and showed that it is a young star that should not be there. This is a completely different topic, more of astrophysical interest. It was quite interesting. They said it's a paradox of youth. There's a very young star orbiting the massive black hole. How can that be? Because these young stars cannot form there. But Andrea Ghez presented these orbits already in conferences before the Nature article was published. So this work was really done at the same time by both groups. And it was actually massively important that there were two independent groups working on that, because it's such a crucial work. And this is now to illustrate, this is actually real images now in a time sequence, and they're well aligned. And here you see how the stars are moving. And SO2 is this one star with the best measured orbit. And you see nicely how the stuff moves. The quality of the images changes strongly as a function of time, because this is basically technological progress. And you see how stars move around the black hole at the center of the Milky Way. Now, this happened 10 years ago. We now have dozens of stars where we have measured the orbit, not just one. This one star from 2002 still is the best measurement, but they have dozens of stars now. And this means that you can actually make precision measurements now. I think it's getting a bit long, my talk, so I'm gonna skip over a part here, because I've been kind of telling, yeah, we measure positions, we have velocities, and we know there's a black hole. So I have a small section here about the nitty-gritty work, which I mentioned already. The big problem in this whole is the reframe of reference. Basically, most energy of both teams went into how to have accurate measurements. So you all know these things. You can have low accuracy and low precision on your measurements, low accuracy and high precision, high accuracy but low precision, but what you want is high accuracy and high precision. And this is where basically the teams really have been working like hell, because it's very difficult to make accurate and precise measurement when everything is moving. And this is basically where everything is going. And now that we know there's a black hole, you actually want to measure and test general relativity there. And you have to make an even greater effort now with understanding, with respect to what am I doing my measurements actually? Where is the 0.0? Where are my rulers in space? Very, very hard problem. And you basically need to be stable to 0.02 milli-arc seconds per year. It's roughly equivalent to if you have a football match on the moon and you know whether the football is inside the goal posts or outside. This is what you have to be able to do, and this is very hard to achieve. I'm not going to bore you with the details here. I'm going to skip over all this. Here is an interesting thing. So, for example, if you have I've always mentioned Kepler orbits. Kepler orbits are always closed, so the object always returns to the same point on this orbit. This is, of course, wrong because Albert Einstein in general relativity tells you that orbits close to a strong mass are not closed, they're Rosetta-shaped. It's the famous problem of the precession of the planet Mercury. Mercury does not move on a closed ellipse around the sun because of relativistic effects. So this is one of the things that you want to measure in the galactic center. So if the star does several orbits around the black hole and the orbit does not close, that's nice. So you say, okay, great, I've measured relativistic effects. The problem though, it's easy to get fooled if your measurements are not good. So on the left-hand side, you see here a nice picture from an article from Shoko Sakai from UCLA. So if you use a bad reference frame and all these data points, all these circles actually points over time, the star goes around the black hole, comes back, and actually does not return to the same point. But this is purely a problem of your measurement accuracy. A few years later, and a few years of work into that, now the orbit really is closed, and that's just a sign of working on your frame of reference. That's not even real physics in there. It's just a huge amount of methodological effort, and it's extreme work. Nevertheless, now we're in the possibility to do high precision measurements. So we know now the distance of this black hole to precision and accuracy of about 1%, and the same thing with its mass. I know you work on material sciences, so a precision or an accuracy of 1% does not sound impressive, but we're in astrophysics here, and in astrophysics, the typical errors are 30%. So 1% is absolutely amazing. So what's going up? What has been opened now through these measurements? So now we know we have a massive black hole at the center of the Milky Way. Of course, now the big holy next step or the next grail is to test general relativity. I mean, in the end, physics always tries to, currently the big physics quest is to unify quantum physics with gravitational physics. And we know that black holes are exactly the point where both of them break down. We know that Einstein, or basically that both of them cannot work at the same time. So black holes are super interesting because they give us an extreme environment. We have now lots of orbits of stars around the black hole, and we have one star that is still the first star of which we discovered the orbit. That is really remarkable because it approaches the black hole so far that it gets actually to a significant fraction of the speed of light. So as you can see here on this animation, this object reaches roughly 3% of the speed of light. This object is a star that is 20 times as massive as the sun. This is truly awesome energies that are involved here. There's nothing that is in the nearby universe that remotely matches these energies. It also means you're in a highly relativistic regime. You cannot do these kind of tests on Earth. A geosynchronous satellite moves too slow, and even binary pulsars, so binary neutron stars that emit radio pulses towards us that are great laboratories, they don't approach anything like that. So we have a unique thing here at the center of the Milky Way. So the groups of Andrea Ghez and Reinhard Genzel now want to do better measurements. 2018, 16 years after the initial discovery of the orbit, the star came back on its orbit around the black hole, and both teams were ready to do more measurements. This time they wanted to show the equivalence principle, basically meaning that a free-falling laboratory is equivalent to one at rest. They did it. And just to show you again why this is so important, if you have the logarithm of the mass of an object here, and this is a logarithm of the gravitational potential, which kind of gives you an idea how strong relativistic effects are. In a laboratory on Earth, you're here at this dot. If you do the precession of Mercury around the sun, you're here. This is neutron stars, double pulsars in the universe, but with this star at the center of the galaxy, you are in a completely unprobed regime. So I'm going to skip this and just tell you that in fact, both teams have shown that the equivalence principle holds around this black hole. It has been measured with spectroscopy. I'm not going to in there. Both teams showed it works. This is just an illustration of what has happened. So the black hole approaches the black hole, and when it's close to the black hole, any clock on the star goes slower, because first of all, the star is moving at 3% of the speed of light. So because of special relativity, the clocks are moving slower compared to Earth. And it's also deep in the gravitational potential of a black hole. So due to general relativities, the clocks also go slower. And this is can be measured because of a redshift of a spectral line on the star, and that has been measured. The next test will be try to measure the metrics, go to higher effects of general relativity. For this, the European group has a unique advantage. So the European Very Large Telescope has an infrastructure that is called VLTI interferometer. So actually there's an interferometric delay tunnel. So one can use these 8-meter telescopes as if one had a 130-meter telescope, which gives you absolutely marvelous precision. And they have already used this to show that the orbit of the star, I'm not going to detail here, deviates from a Kepler orbit. And actually we have a precision, so it's a Rosetta-shaped orbit, it doesn't close. This is just an illustration of the effect that has been measured. And the UCLA team is now trying to match these measurements. Again, the UCLA team has not yet done these measurements. They have different equipment. They cannot be as precise, but I know them and they are very much invested in systematics. And all this work is always systematics. So it remains to be seen whether the other group can confirm this measurement. This is so complicated work that it's very important that you have independent confirmation from another group. So this is all. I hope I have not bored you with too much astrophysics. So again, congratulations to Reinhard Genzel and to Andrea Ghez, the 2 Nobel laureates. Thank you for having the patience to listen to me. I'm open to any questions you may have now.
Thank you. Thank you very much for your nice speech. It's really spectacular images of the universe. And now is time for question. If you have any question, you can just unmute your microphone and make the question to our speaker.
I have a question.
Okay.
A very nice talk, Reinhard. Thank you very much. Well, I mean, you said that this energy is the most energetic event you can measure now in the I understood that, I don't know, but there are many black holes out there, and in the closest galaxy, is it not possible now with the accuracy and the methodology to observe this in another black hole, in a different galaxy?
No, we can, okay, yes and no, it depends. This kind of work, what is being done in the Milky Way, is impossible to do in any other galaxy, simply because the nearest galaxy where we could do this work is the Andromeda Galaxy. The center of the Andromeda Galaxy is roughly 100 times as far away as the center of the Milky Way. So your angular resolution is 100 times less. You cannot do this. It's different if you want to do different kind of work. For example, the Event Horizon Telescope is measuring making radio images of black holes. It has an angular resolution of 20 micro arc seconds, and it can try. They're actually probably maybe publishing something on the Milky Way this year, and they have been doing this kind of they have not been measuring stellar motions, because you cannot do this in the radio. The stars do not shine bright in radio wavelengths, but they've created this image of the black hole in the galaxy M87. The funny thing is M87 is 1,000 times further away than the center of the Milky Way, but the black hole in M87 is 1,000 times more massive. But for the radio Event Horizon Telescope, there's only these 2 objects, M87 and Sagittarius Star, where they can use this technique. And if you want to measure how stars move around the black hole, you can do this for the aggregate of stars in other galaxies. So you can actually use spectrometers and see how the mean motion of stars at the center of nearby galaxies shows you that there must be a lot of mass enclosed in a small volume. So you can measure the masses of other massive black holes in other galaxies. However, you cannot convince a skeptic that those must be black holes. This you can only do at the center of the Milky Way, because only in the center of the Milky Way you can get so close and measure the orbits of individual stars.
Okay, thank you.
Any more questions? I would like to make a question also. In your opinion, what is the most limiting aspect you have in your research? The technology for measuring, or?
The most limiting aspect in my research?
Yeah.
I'm an observational astrophysicist, so it's always technology that limits us.
Technology.
It's always technology. It's always been pushed forward. We always want bigger telescopes.
Yeah, but
so actually, yeah, the next step is going to, so we have this interferometry now, and also the next step, actually Europeans are becoming leading in ground-based astrophysics. So the European Southern Observatory is already building a next, the so-called extremely large telescope, which will have a 39-meter primary mirror, composed then of 1,000 individual mirrors. So that's the next step.
So next step to measure more orbits is to have a bigger telescope.
Yes, you need the angular resolution. You can only have the angular resolution with a big telescope. And then, of course, all the additional technology to overcome the problems of the Earth's atmosphere. And it's quite interesting because in this kind of field of work, for example, going to space is not necessarily the solution, because you cannot put big telescopes in space. The biggest one to put in space, if we are lucky, the James Webb Space Telescope will be launched in September finally, but it only has a 6-meter mirror. And you want 10-meter or larger telescopes for this kind of work.
Okay, thank you.
And of course, detector technology is very important. I mean, your material science, so infrared detectors are massively important. Low noise infrared detectors, fast infrared detectors. But a huge progress has been done on this also in the last 30 years.
Okay, thank you very much. Any more questions? Anymore?
It's okay. I mean,
I think
it's very hard from other fields. I'm used to that.
And it's very far of our research work, so maybe it's only curiosities, the question we have in this area.
Yeah.
So.
Yes, so stay tuned. Exciting stuff is happening there all the time. You will hear from that again. So probably, as I said, the next big thing is probably that the Event Horizon Telescope team is going to show an image of this black hole at the center of the Milky Way this year, I think.
Oh, fantastic.
That will go through the press, definitely. So you will not overlook that easily. We also have people in the IAA, if you want to hear about that. So there's people also strongly involved from my institute. Okay.
It's fantastic now. Yes, we are attending this news. Okay.
So thank you again very much for the invitation.
Thank you very much for coming to our colloquium in our institute. Thank you for this really nice talk and the spectacular images you have show us. And I would like to remind you that we will have another colloquium in April, and now it will be dedicated to the Nobel Prize in Chemistry. Also, if you want to attend this one, you are all welcome.
Thank you.
Thank you very much for attending our colloquium, and thank you for your speech.
Thank you very much. It has been my pleasure. Bye-bye.
A pleasure also for us. Very congratulations for your work. Thank you. Bye.